Okay, this is video 4 on conditional probability. We are talking about Bayes' theorem in this video. Before we actually talk about Bayes' theorem, there is another law that is important, and we need to understand that first before we move on to Bayes' theorem. So this is called law of total probability. It expresses the total probability of an outcome because that particular outcome can be realized using different distinct events that are mutually exhaustive and exclusive, right? So for any event B, if that event can be described in terms of multiple other events that are mutually exclusive and exhaustive, then the probability of B can be expressed as something like this, right? So this is not clear yet, but let's look at a visual of how this breaks down, and then it'll be easier for us to understand. Okay, so let's assume this is my sample space and this is some event E inside, right? And now I'm interested in the probability of A, right? From the multiplication rule and also from the visual itself, it's clear that the probability of A can be found out by finding the probability of this event A and the sample space, right? But now I see that this event A is divided into multiple parts because there is a different sample space for each part of A. And like each of these parts are mutually exclusive and they're exhaustive because they actually make up the event A, right? So I can write down that the probability of event A is starting from I equals 1 to n because there are n of these. Let's assume there are n of these. The picture shows only 4, but let's assume there are n of these parts into which A is divided. And from the law of the multiplication rule, and also from our knowledge of probability, I can say that this is probability of S of I and A. The sum of the probabilities wherever this intersection is happening, right? Both S of I and A, right? Because there is this occurrence of A in every S1, like in every S of I, right? Now, from the multiplication rule, I know that this particular expression can also be expressed as something like this. I is from 1 to n, and then probability of A given S of I times the probability of S of I, right? This is exactly what the law of total probability states, right? If we are interested in finding the probability of some event A, and we know that this event A is conditioned upon multiple other events, or there is this there are these common outcomes such that the events, all these like A's, are conditioned on those, right? So then we can find each of them separately and just like add them up. Okay, so let's look at an example to understand what exactly this means. Okay, suppose that we have two bags. One has 4 red and 6 white balls, okay, and the other has 6 red and 4 whites. So when we toss a fair coin, if we get a heads, pick a random ball from the first bag. If we get a tails, pick from the second. What is the probability of getting a red ball? Now, I know that I'm interested in getting a red, but that is possible in 2 different ways, right? Either I get a heads and then I pick a red, or I get a tails and then I pick a red, right? So this could be further written down using the law of total probability as probability of getting a red when I get a heads times probability of getting a heads plus probability of getting a red when I get a tails times probability of getting a tails, which in this case is 4 over 10 because there are 4 red balls, and then getting the probability of getting a heads is half. Either you can get a heads or a tail. And then this is because we have 6 red balls in the second bag, right, out of 10, and then again 1 over 2 and this gives us 1/2. Okay, problems related to the law of total probability can also be solved using the outcome tree method, and they're sometimes easier to um, organize things when we're using the law of total probability. For example, in this case, I can say I start at this point, I either get a heads or a tails. And just a reminder, these are the edges in the tree method where I keep adding the subsequent probabilities. So there is 1/2 chance of getting a heads and 1/2 of getting a tails. If I get a heads, I can pick red balls and or I would say white balls. The probability of picking a red ball, 4/10, 6/10. Similarly here, I can pick a red or a white. Sometimes it's easier to visualize also, as you can see the subsequent steps for each case. And then this is 4/10, right? And then remember how the outcome tree method works. We have to write the entire outcome, which is this, in this case, h of r, hw, sorry, not h of, but hr, and then tr, and then tw, right? So these are the outcomes. And I'm only interested in the outcomes whenever there's a red ball, right? So maybe I'm not even interested in where the whites are. So let me see what's this. And remember, this used to be a weighted average. So here it's going to be 1/2 times 4/10, right? And then here it's going to be 1/2 times 6/10. And so the desired probability of getting a red is going to be the sum of these two, which is again 1/2. Okay, so this finishes our discussion on the law of total probability. This is extremely useful, especially when we are looking at Bayes' theorem. So now let's actually look at what Bayesian probability, probably you might have come across this term, and what exactly that is. So probability refers to frequency many times. We have seen that, right? How many number of people given a larger set do this? So that's like thinking of probability in terms of frequency. Now, Bayesian probability is slightly different because it's a measure of a state of knowledge. Now, this is not super clear right now, but just think about it that it quantifies uncertainty, and it also helps us reason that uncertainty, right? So a Bayesian model, whenever you hear about this term Bayesian model, it's something that's continuously updated as we get more information, right? So the idea essentially comes up from whatever we have discussed until now, conditional probability, law of total probability, but let's see how, like, what exactly is Bayes' theorem. Okay, so Bayes' theorem shows a relationship between conditional probability and its inverse. I wouldn't go into this yet, but we'll understand that when we are solving problems. So let's not confuse ourselves yet, but actually look at what Bayes' theorem says, right? So it allows us to answer questions such as these. Given that someone tests positive for having a disease, what is the probability that they actually do have the disease? Because tests might not be accurate, right? Or given that someone tests negative for a given disease, what is the probability that they do have the disease, right? Because the test has some known level of accuracy. We cannot completely rely on that test. And so we really need to know what is the probability that I actually have or do not have that disease, right? So questions like these are answered using Bayes' theorem, and it has applications in medicine, as you can see, law, AI, engineering, and other diverse areas. So let's look at how it is stated, right? So mathematically, it's stated something like this. This is what Bayes' theorem says. We are interested in, let's say, the probability of A given B, which is also called the posterior many times, right? Based on something that we already know, which is the prior. So I already know if probability of A on its own, like how likely is the probability of A on its own. So I already know that, which is probability of A, right? And then I'm able to somehow compute probability of B. In most of the cases, this is computed using the law of total probability. So this again means how likely B is on its own, right? And then many times from other experiments, from other knowledge, from prior knowledge, we already know what happens um, if given A, B, like we are interested in the probability of B, right? So this in most of the situations is known, and it's also called the conditional, right? So this is what Bayes' theorem, this is how Bayes' theorem is stated mathematically, right? So it's a way of finding a probability when we know other probabilities for sure, right? Okay, let's look at this example to understand what Bayes' theorem actually does. Okay, suppose that Joe is late one day to work, for work obviously, and his boss wishes to estimate the probability that he traveled to work that day by car. Now, there is some data that's available to us. So the mode of transport that Joe uses is either car or bus or train, and the probability of using each one of no, that's not of using. That's the probability that he is late. Is this? Are these? So he's late 50% when he's using the car. He's late 20% when he's using the bus, and he's late 1% when he's using the train. Okay, so his boss wishes to estimate the probability that he traveled to work that day by car. So basically, the boss is interested in finding out that he traveled by car given that he's late, right? Okay, so in this situation, I do have some information about the probability that the person is late given car, um, because this information is already there, right? So this is something that's available to me. I also can calculate the probability okay, so we don't know that, but there is some additional information given here. So he does not know which mode of transport Bob usually uses, so he gives a prior probability of 1 in 3 to each of the 3 possibilities. So that's good. So now we are saying that the probability of bus is equal to the probability of car, because we need that, right? Is equal to the probability of train, and it's 1/3. Right, so this is on its own, the probability on its own for each of these 3 modes of transportation, and we are interested in probability that the person that the person is travel by car given that he's late. We already know that he's late. Now, what are all these that are given here? Right, so these are actually the probabilities that when the person is late, given that he was traveling by car, right? This is 0.5. Probability that the person is late given that he was traveling by bus, right, which is 0.2. The probability that the person is late given that he was traveling by train, which is 0.01, right? So this is extremely low. So we have all this information. All we are interested in is probability of car given late. So we can apply Bayes' theorem, which is, let me restate it here in terms of our problem, which is car given late, right? So just applying the formula, which is probability of late given car, right? So I'm interested in the posterior. I have the conditional, and then I have probability of car, and then the probability of late. So I do not have the probability of late if you look at it. I have the probability of car, I have the probability of late given car. But using the law of total probability, because he, like, of all the modes of transport he's using, we have the probabilities of when he's traveling by car, the percentage that he's late. We have all that information. So I can use the law of total probability to get that. Right, so this is already known, right? And this is also known. Now, to get the probability that he's late, get the probability that he's late given he's using car times the probability of car, right? Plus probability late given bus times probability bus, plus probability that the person is late given train times the probability that he's traveling by train, right? So I can get this 0.5 times 1/3, and then we know the rest of them, right? So this is 0.5 times 1/3 plus, this is what, 0.2, I remember, times 1 over 3 plus 0.01 times 1 over 3, which, by the way, I calculated, comes equal to 0.7042. Okay, so this demonstrates how we use the Bayes theorem. Given that we have certain information available, we want to update something and we want to arrive at some conclusion, which was what is the probability of car given that the person is late, of using a car given that the person is late. Let's look at more examples to understand this better, and in fact I'll continue this in the next video and also look at more complex problems.